Okay, so we are going to continue our work with circles. We're going to actually do that with some familiar shapes, some things that we've seen before. We're going to introduce a couple of new terms here, well, at least one new term that you haven't seen before. We've seen the word inscribed before, but the word circumscribed is probably something that we haven't seen to this point. So let's take a look at that word real quick just so we can kind of break down what it means. If you look at the first few letters here, that should actually look familiar because it's the same first few letters that goes into circumference. And if you think about the circumference of a circle, you are literally talking about the whole outside of the circle. Okay, the actual ring, the circle part, that is the circumference. So it's basically what is on the outside. So the word circumscribed actually means to surround or be around, outside of. So the circle that we show here is what is called a circumscribed circle because it is a circle that surrounds a triangle, or it could be any other figure, but a triangle in this case, and the circle containing the triangle such that the vertices of the triangle are on the circle. So here is a vertex, here's a vertex, here's a vertex. They all hit the circle. Okay, that's the important part. So when you have a circumscribed circle, which is what this one is, the circle must hit all of the different corners of the inside object. In this case, again, it's a triangle, so it's got to hit all of the vertexes or vertices of the inside triangle. That makes something circumscribed. Now, if you look at the first couple of letters of the previous one, which we have seen before, inscribed, the word in means inside. So in this case, in our second drawing, the circle is going to be inside of the object. In this case, it's going to be inside of the circle. So a circle that is inside a triangle. In this case, what you should notice is that circle has to hit all of the sides of the triangle. So in this case, it hits that part here, that part here, that part here. It's got to hit all the different sides of the triangle. Or, I mean, if this was a hexagon, which has 6 sides, then the circle would actually have to hit all 6 sides. Likewise, in this previous example, if there was a hexagon built into the middle of the circle, so you would have a circumscribed circle around the hexagon, the circle would have to hit all 6 vertexes or vertices of the hexagon, if that was the case. Now we're just dealing with triangles here, but just to let you know, that's what has to happen. So this one is called inscribed, again, because um, the circle is inside of the triangle or inside of the polygon. So that is inscribed. Okay, any of that doesn't make sense, please go back, watch it over again if you need to, but that's what that means. That's our definitions. Today, specifically in this lesson, we are going to be focusing on circumscribed and how that relates to the angles and the arcs and things like that. So I can give you what the rules are going to be for these, but I kind of want to show it, so maybe it'll make sense. That way, maybe you can piece some things together. So we have to remember a couple things that we've already done in the past. This first figure here with the triangle ABC in it, we've already seen stuff like this before. But now let's take a look at what's going on here. One of the things we should notice is that the line segment between A and B is the diameter of the circle. So right there, not exactly a straight line that I drew, but that's the diameter. What we know about a diameter is that it splits a circle in half, which means that this arc over here between A and B, I'm doing my best to trace it there, we know that that is half of the circle. And the arc measure for half of the circle is 180 degrees. So now let's talk about why that's important. Well, it's important because what we should see is that if you look at letter C, there's an angle that's made here, right there at C. There's an angle. And if I follow the lines of that triangle all the way out to the point where they hit the circle, you can see that they intersect the circle at points A and B. Well, the angle that's made here, if we remember, this is what is called an inscribed angle, because the angle actually hits the circle. It's not something which is made from the center, like this one right here. That would be a central angle. That's not what we have here. We have an inscribed angle because the angle hits some part of the circle. The inscribed angle is going to be exactly half of the arc that it hits. Well, the arc that it hits is that red 180-degree arc, which means that the angle here at C, which is half of that, has to be 90. And we know a 90-degree angle is a right angle, and we use the little box to notate that. Okay, so all of this is great, but this isn't actually even the most important part about the whole thing. We should remember that all of the angles within a triangle add up to 180 degrees. Well, I already have 90 degrees right there. I have two angles left. I have this angle and I have this angle down here. Well, those two angles right there have to make up the remaining part of 180. Well, if the one with the box is already 90, then the ones with the orange, the two remaining angles, also have to add up to 90 because they have to make the other part of 180. That's the important part right here. So the two angles that are not the 90-degree angle, or the two angles basically that are sitting on the diameter, so these touch the diameter, are going to be having to add up to 90 degrees. So now we'll actually write the rule. First of all, the shape that was inside the triangle, inside the circle is a triangle. That's the shape. And the rule is, if the diameter is the hypotenuse, then the two angles that touch the diameter add to 90 degrees. So basically, angle B and angle A here have to add up to 90 degrees. Now, the interesting thing about this, if you really think about it, if I move C from where it was, maybe I put it up over here, maybe that's C, and I were to draw a new triangle, and you don't have to draw this on your paper, but if I were to draw a new triangle hitting A and B, anywhere that I put C, as long as A to B is the diameter, is going to create a right angle. And again, because A to B, the arc is 180, so half of that is going to be 90. So it really doesn't make any difference where that C is. C could be here, it could be here, it could be way over here, it could be here. It doesn't make any difference. That's always going to give you a right angle. So the other two angles on the inside of the triangle are going to have to add up to 90 degrees. That's always the case there. All right, the other one, the rule is much shorter, and it's probably a little bit easier. The shape that is inside of the circle. I've asked this several times, and people are like, oh, it's a square. Well, it doesn't really look like a square because you'd have to have all the angles be right angles, and they certainly don't look like that. Although we don't know it for sure because drawings can be just a little deceiving. Some people have said it's a rhombus. Again, it could be a rhombus, although it doesn't look like it, because to be a rhombus, all four of the sides would have to be equal. But the key is, and it's much more general than that, it's got four sides. If you remember back to what we called these, word four, quadrilateral. So the shape of this is a quadrilateral. And that's that ABCD shape inside the circle. That is a quadrilateral. All right, so again, let's see what's going on here. If I were just to look at the arc formed from A to C, I'm going to go this direction. I'm going to go this direction because I said the arc from A to C. I did not include the B, even though there's a B there. But it looks like A to C is a little bit less than half of the circle. That doesn't look like it's a completely straight across. It's close, but it doesn't look like it's a diameter. But what I should know is that the angle down here hits A and C and opens up to that arc. So whatever this angle is right here, it's going to be half of that blue arc. Okay, I'm not writing that, but it would be half of the blue arc. So now let's look at the other side. Let's go from A to C, but going the other way. So technically this would probably be a major arc, ADC, because it looks like it is greater than 180 degrees. Well, the angle that opens up to that green one is this one right here. We don't necessarily know that these are the same, so we have to put different markings on there because B and D might be completely different. They could be the same, but they could be different. But here's the key. If you look at the blue arc and the green arc and add those together, it should look like it does the whole circle. And if it does the whole circle, then that means the entire circle is 360 degrees. If we cut that in half, whatever B and D are, they will add up to half of a full circle, which is 180 degrees. So what that tells us is that opposite angles add to 180 degrees. Which also means that A and C, because those are across from each other, A and C will also add up to 180 degrees. All right, let's look at a few examples, and hopefully you'll see that this isn't all that bad. Again, if there's anything you don't understand, go back, watch it again, see if it makes sense, ask a friend, ask a neighbor, whatever it takes, or ask me when you get the chance. All right, so our first example says that the measure of angle D is 160 degrees. So I'm just going to find angle D on here, and I'm going to label that. That one's up here. That's 160 degrees. It tells us to find all the other measures of, it's supposed to say quadrilateral. It looks like that got cut off, but that should be quadrilateral. Well, according to what we just talked about, because that is a quadrilateral, opposite angles are going to add up to 180 degrees. So the opposite one from D, if I basically were to draw something to the other side, looks like it is angle B. So 160 plus some number has to add up to angle B, or you could simply do 180 minus 160, and what you should get, angle B, is to be 20. Okay, so that's two of them. Now we got to find the other two. Well, one of the symbols on here shows us this angle right here, and that's only given, oops, this symbol right here is one arc. This symbol right here is one arc, which means that those two things are congruent. They are the same. And since that's the case, I think I kind of erased my numbers there. Let me write that 20 in there again. If that's the case, because those two, both of those angles have green arcs where E and B are, that means that E is also 20 degrees. And then we know the one across from that has to add up to 180, which then makes that one 160 degrees. Write that a little better, 160 degrees. So C is 160 degrees. It isn't always going to work out where both of the both of the angles are going to be exactly the same. But in this case, it did. And it's because the quadrilateral in there is actually a trapezoid, which is symmetrical. Again, it doesn't always work out that way. But that's how you can kind of piece those things together. Okay, next example. In circle G, we are given that DE is the diameter of the triangle, of the circle, and we have a triangle on the inside. So we want to find the measure of angle D. Well, angle D is given by that expression right there. So we need to find X so that we can substitute that in and get an actual number out of all this. Well, because we have the diameter and it's a triangle, we know that this angle right here and this angle right here have to add up to 90 degrees. So I have an expression for angle D, which is 2x plus 6. If I add that to 8x plus 4, we know that that has to now equal 90 degrees. And now we have a way to solve for x. Combine our like terms. I got a 2x and an 8x here. That's going to give me 10x. The 6 and the 4 add up to 10. And that has to equal to 90. We can now subtract 10 on both sides. Again, this is just the basic algebra at this point. So we have 10x equals 80. And we'll divide both sides by 10, which should give us that x equals 8. Again, that's not the final answer because they are looking for angle D. So angle D is going to be 2 times 8 plus 6. 2 times 8 is 16, plus 6 more is 22. So that is a 22-degree angle. Technically, we could find out what angle E is as well. We could either plug 8 into that one and figure that out, or since we already know that this piece right here is a right angle, that's 90 degrees, we could do 90 plus the 22 and then subtract that from 180 to get the missing angle. It didn't ask us to do that, but we could do it if we needed to. All right, last example. We want to find out the measure of angle BCD in the figure to the right. So we have to find angle BCD first. So if you start at B, go all the way down to C, and then up to D, we are talking about this angle right here, which is represented by 3x plus 7. All right, so in order for us to find that, we still need to find the value of x. Well, this is a quadrilateral, which is inside of the circle, so we know that these opposite angles right here, the ones across from each other, have to add up to 180 degrees because it's a quadrilateral. So now I have an equation. 2x plus 3 plus 3x plus 7 has to add up to 180 degrees. Notice I didn't need that 4x on the right-hand side at all in this. It was just an extra piece of information. All right, combining like terms, 2x and 3x is 5x. 3 plus 7 is 10, is equal to 180. And again, here's our algebra. We'll subtract 10 on both sides, giving us 5x equals 170, dividing both sides by 5. Let's see, 170 divided by 5 is going to end up being 34. So, again, we're not done with the problem. That's great that we found that value of x, but we want the measure of angle BCD. Measure of angle BCD. What we're going to get is we're going to get 3 times 34 plus 7. 3 times 34 is 102 plus 7 more is 109. Again, you can pop that in your calculator to double check that, but that is measure of angle BCD. Okay, we could actually plug the x value back into the one at the top to figure out what angle that is if it asked for it, for where angle E is. It didn't ask for it, but we could. Or we know that 109 plus whatever that angle is has to add up to 180. So we could just take away 109 from 180 if we had to. And we could then find the measure of angle B because we do have the x value. So we could just plug that x value into B, which is 4 times 34 to get that angle. And then we could find the missing D angle, which didn't have anything written there because we'd have all the other pieces. So a lot of stuff we could do with this if necessary. All right, that should take care of it. That should be the end of the lesson for this one. Again, if you didn't catch anything or something didn't make sense, go back, try and watch it again, figure it out, or next time I'm there, you can ask questions. All right.